Hello everyone, and I hope all of you are doing well. And today this is our lecture 3, and in lecture 3 we are going to start a very new concept or a new chapter, which is energy. And in this chapter we will also see the first law of thermodynamics, which is nothing but conservation of energy. Okay, so to start with, let us see what is energy. And energy, why are we discussing energy here? Because energy is very fundamental to thermodynamics, very fundamental concept in thermodynamics. Okay. And while we were defining the term thermodynamics, we also saw that thermodynamics was nothing but a science of energy. So thermodynamics is also known as science of energy. It's a storage, conversion, and transfer. Okay. Now energy storage has various forms, and we will see them in detail. So energy storage can be in terms of kinetic energy, then gravitational potential energy, and we will see in thermodynamics how this energy is also important. So there is another form of energy which is very important in thermodynamics, defined by internal energy, and we generally denote it by a symbol U. So we will see these things in detail. So to start with, let us go to mechanical concept of energy. And for mechanical concept of energy, here you can see a diagram where a body, I have shown a body, a path, then various forces acting on it. And if we want to write the equation of work or the force, so here Fs can be written as m dv dt, and this is nothing but second law, Newton's second law of motion. And this m dv dt can be further broken down into m dv ds into ds dt, and we know that ds dt is nothing but v, so this can be further broken down, reduced to mv dv ds. So if it is something like this, and if it has moved from distance s1 to s2, then we can say the work done is integration of this force dot ds from s1 to s2, and here I have taken ds to the left side, and the right side becomes integration of mv dv to v2. On integration, we can say this is nothing but half mv v2 square minus v1 square. And this thing, so the right side of this thing, or to be more precise, this half mv square term is nothing but it is known as kinetic energy. So here we just saw that work done given by integration of f dot ds s1 to s2 is nothing but equal to change in kinetic energy, and this delta always means final minus initial. Okay, so here from here we can say that kinetic energy is related to work. and that's how we define kinetic energy. Now there is another kind of energy which is called potential energy, and for potential energy again I have taken this diagram to explain the potential energy. Here if you see, this R is a resultant force and mg is the gravitational force, and if we really want to calculate the work done here, so we can see it like here the force is R minus mg, because R is acting upward and mg is acting downwards, and if we see the distance is z2 minus z1. So we need to integrate for the work transfer, we need to integrate it like this r dz, r dz from z1 to z2, and then this mg is acting downwards, so mg dz z1 to z2, and then we already know this. Okay, and this term here is actually potential energy. So this mg z2 minus z1 is actually change in potential energy. Change in potential energy. And this is just for our understanding. So what is kinetic energy? Kinetic energy because of the motion like this V2 and V1, and then potential energy is due to position. So elevation like Z2 and Z1. So in this way we define kinetic energy and potential energy. Now comes the concept of units of energy. So we just saw that energy can be like work done, and if you see work done, so work done is force into distance, which is Newton into meter, and we also call it as joule, and the symbolic form is just capital J. Now we need to broaden our understanding of work in thermodynamics. So what we just saw, W work is S1 S2 and force into this. However, in thermodynamics we need to see the work done due to expansion or compression of gas, then extension of solid bar, or stretching of liquid film. We will see each one of it. Now there comes a concept of sign convention, and this is pretty much everywhere in the thermodynamics. So whenever we are going to write the first law of thermodynamics for any system or anything, then we need to consider the sign convention of work done. So sign convention of work done is work done is greater than 0 if done by the system, the work done is by the system, and work done is less than 0 if work is done on the system. So if you see the example here in this figure, you see that battery is supplying some current, and due to which the shaft rotates, and then it is rotating a paddle wheel, because of which this gas, there is some energy transferred to the gas. And if we consider system B and system A, then for system B the work is done by the system. So if the work done by the system, so for system B the work done is positive for B, and for system A the work is actually done on the system. So for A, work done is actually negative. And there is a definition to thermodynamic work, and we can call it as like, and we can say it or we can summarize it as work is done by a system on its surrounding if the sole effect, and this is a kind of definition, so if the sole effect on everything external to the system could have been raising a weight, could have been raising of a weight. Now two things here. So one thing is, this is just a kind of representation. So it doesn't mean that you need to raise a weight, but it just means that force is acting through a distance. For example, while compressing a gas, so force is acting through a system. And you should also note that could have been, so it is not like strictly, so not strictly. And if you see from the definition of work, where we defined work as this thing, and from here we can say that in the definition of work there is one term ds, which is nothing but displacement, and we will see it later, but right now I am focusing on this concept also, so that once we discuss it later we can come back to it and we can appreciate that yes, this is what it means. So actually work depends on path, and hence work is not a property. Now what does it mean? So you cannot say that work at a state 1, like what we used to say during our volume or temperature. So you can actually define volume at a state 1 or volume at a state 2, but you cannot define work like that. For work, we also represent it with some inexact differential. So suppose 2, if you integrate this, so this del is actually put in front of the W to represent it as inexact differential. This is also one feature of this thermodynamic work. Okay. So now I will summarize few of the things for work, which is very important. So work actually is an exact differential, is represented by an exact differential. It's not a property. Work is not a property because you know that this ds and this depends on the displacement, so not a property. It depends depends on path. Okay, then you can write something like this, 1 to 2, this is correct, but you cannot write something like this is incorrect. Okay, so and we will see later also that yes, how work is a path dependent function once we discuss the examples. So now let us go to some calculation where we are trying to calculate the expansion or compression work. So if you see this figure, here we have a piston cylinder arrangement, cylinder and piston arrangement, you can see, and then there is some gas which is applying some force on the piston, and that force can be calculated as force equal to PA. Now this is pressure of gas, A is the area of cross section of the piston, and then it travels with some distance like this, dx. And if you want to calculate the work done here, so we can say del W is F dot dx. Now this F is nothing but PA, so del W can be written as PA dx, and we know that area into distance is volume, so this del W will become P dV. And if you want to get the work done, so you have to integrate it, so this will become like del W equal to W equal to V1 V2, this is nothing but the volume representation of that, P dV. So this is the work done for a closed system. You see here, this is the closed system, and this is work done for a closed system during expansion or compression. Now there comes a concept of quasi-equilibrium process. So consider this kind of setting where you have gas or liquid in the system, and then on the cover you have like all these smaller particles, and suppose if I remove these particles one by one, then the departure from thermodynamic equilibrium is thermodynamic equilibrium is infinitesimal. So it is always, even if I remove one of the pebbles here from the top cover, the system will always be in thermodynamic equilibrium. So these kind of process where it is slow and you can switch between thermodynamic equilibrium quite easily, you can say that you can say these process as quasi-equilibrium processes, and they have certain importance in thermodynamics, and we will see that to define the work or a reversible process, we generally consider it as quasi-equilibrium process, so that from state 1 you can easily go to a state 2 and you know the path. So what I mean is, if I try to expand this gas, very slowly, then you can actually draw this path between state 1 and 2 by a very smooth line, and then we can directly calculate the area under this curve as P dV, because you know the equation now for this pressure in terms of volume, then you can integrate it and get the work done. And as we mentioned earlier, that work is a path dependent thing, so that can be understood from this figure. So suppose from state 1 to state 2 we can go via path A or path B, and if you see the area under the curve, then you can easily identify that area under curve 1B2 is greater than area under 1A2, and then we can write work done in W1A2 is actually greater than work done by this process when following path 1B. Sorry, not this, but work done following path 1B2 is greater than work done following path 1A2. Okay. Now we need to further broaden the concept of energy in thermodynamics, and we just saw that only two kinds of energy here, which is like kinetic energy and then gravitational potential energy. We already discussed these things, gravitational potential energy. But if you see the example I have shown here, so here we have a battery and we have a paddle wheel arrangement. So we can charge this battery and then we can rotate this shaft to increase the energy of the gas. So energy of the gas can be increased, right? But these two things cannot be accounted for in terms of potential energy and kinetic energy. Okay, and there comes the term which we discussed during our introduction to this chapter, and that thing is internal energy. So all the other kinds of energy which is different from kinetic and potential energy, we call it internal energy, and we represent it by symbol U. So if you want to say total change in energy of a system, so if you want to say, for example, total change in energy of a system, we can say E2 minus E1 equal to U2 minus U1, which is nothing but internal energy, plus K2 minus K1, which is kinetic energy, and then P2 minus P1, which is change in potential energy. So this can be summarized as del E equal to del U plus del Ke plus del Pe. Okay, so this is change in total energy for a system. Now there is another energy which is called heat energy. And so the heat energy thing comes from a concept that all these closed systems they can also interact with the surrounding in a way which is different from work. So if you see here the example, this is the hot plate and a container of gas is kept on this hot plate. So energy of the gas will increase, but here it is not like what we just saw in work transfer or work done, not in terms of work. So here we can say that the energy transfer is, energy transfer is mainly due to temperature difference, and we call it as heat. Okay. Now with heat also comes the sign convention, and the sign convention is just reverse of the work transfer. So for heat transfer is greater than 0 or positive if heat is transferred to the system, and heat transfer is less than 0, which is negative if heat is transferred from the system. And they are convention, they are like from convention. Similar to work transfer, heat is also not a property. So heat is also not a property. And we will discuss the heat transfer modes in the heat and mass transfer course, but just to give it a closer, we know that heat transfer can occur through conduction, and we know for conduction heat transfer rate is equal to Ka dt dx, where K is thermal conductivity, A is the area of cross section, dx is the distance through which this temperature difference is present. Okay, then we know convection heat transfer, which can be given as HA. This is the base temperature of the surface, and then this is the surrounding temperature. Then heat transfer by radiation, and we will discuss all these details in the heat and mass transfer course. Is epsilon sigma A TB4, and this is like the emissivity, which has values between this, and sigma is the constant, which has a value of this watt per meter square. And here you have to take temperature of the base in Kelvin to avoid any discrepancy in calculating the radiative heat transfer. And in the next lecture we will further discuss the energy balance for a closed system. So in next lecture we will see energy balance for closed systems in detail. Till then, that's all for today's lecture. Thank you for attending the class, and keep visiting Mechanical Engineering Gyan. If you are not subscribed, subscribe to the channel and press the bell icon so that you will get all the notifications. So see you in the next lecture. Thank you.